Welcome to 2.1, Summarizing and Organizing Data. And what we're going to do is we're going to organize and summarize data, and we're going to see what kind of ways we can do that. So one of the ways that we're going to be talking about is frequency distributions. We learned in the last chapter about the source of the data, the sampling methods, and some conclusions and implications of incorrect sampling. Now we're going to see the distributions of data, and we're going to organize and summarize the large amounts of the data into tables and graphs so that later on we can analyze it. So our first example, we're going to identify the class width, the class midpoints, the class boundaries, all for this table down here, which is a frequency distribution. What this frequency distribution is summarizing them is the drive-through times. So over here on the left, it has the time in different groupings. We call those classes, and they're the time intervals, and then the frequency that it occurs over there. So if it took an order 75 to 124 seconds to get ordered and into your hand at McDonald's during lunch, that would have occurred 11 times. That's what they mean by the frequency over there. So let's look at these class width, midpoints, class boundaries, all that through some vocabulary. A frequency distribution, that's showing how our data is partitioned among several categories. We call them classes, by listing the categories along with the number or frequency of data values in each of them. So these down this side are called the classes. Around the other side is the frequency in each one, or the amount of number in each one. So frequency is the number of original values that fall into that class. The lower class limits are the smaller numbers that belong to the classes. Those are the first numbers, which are 75, 125, 175, 225, and 275. So our lower class limits. Our upper class limits, as you probably can guess, are the upper values in the classes, which are 124, 174, 224, 274, and 324. Now let's get into a little harder term, class boundary. A class boundary is the number that's used to separate the classes, but it's without the gaps created by the class limits. So what do? We're going to go in between each class. So in between, right here, 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 and here, in between the classes. Halfway between 124 and 125 is 124 and a half. Halfway in between 174 and 175 is 174 and a half. And I think you get the idea there. So halfway in between each of them. Well, we also have to have one in front of our class. So we've got 74 and a half, and one after our class as well. So we have 74.5, it's right lower than our lower class, he's a boundary. Then our 124 and a half, our 174 and a half. These are kind of sloppy, let me move that around a little bit. So 74 and a half, 124 and a half, 174 and a half, and then our next one, 224 and a half, and then 274 and a half, and our last one, 324 and a half. So our class boundaries are in between the classes halfway, so basically on the line there, and what we're looking at, you have to have it surrounding the classes as well. So one lower than the lower limit and one higher than the higher limit. All right, now to our class midpoints. Midpoint values, as you can guess, are the values in the middle of the class. And each midpoint is computed by adding the lower and the upper class limit to each other and dividing by 2. So the midpoint is going to be right here in the middle of the classes. So to get the first one, I would do 75 plus 124 and divide that number by 2, which in this case is going to be 99.5. So I'm going to find the class midpoints of each one of them. The first one's 99.5. Halfway in between 125 and 174 is 149.5. Then comes 199.5, 249.5, and our last one, 299.5. Our class width, it's the difference between two consecutive lower class limits, or the class boundaries as well. So between 75 and 125, 25 minus 75, that's 50. That's our class width. And you probably already noticed that one, that pattern going on. Now, how are we going to construct these frequency distributions, and why do we do it? So first of all, why do we do it? It's so we can summarize large data sets. And so we can analyze the data to see the distribution and identify any outliers. And that way we can have a basis for constructing our graphs as well. So how are we going to make this frequency distribution table? Well, we got some steps to do that. The first thing is we have to select the number of classes. That's usually between 5 and 20. And we want to use it usually by convenience because, well, it makes sense. So we're going to use probably round numbers. So the first thing we're going to do is select how many classes. Then we have to figure out the class width, which remember, that's going to be, the way we're going to find that is our maximum data value. So we're going to figure out the biggest number in our list minus our minimum data value. That's the smallest number in our list. And we're going to divide by the number of classes we choose. So if we go back to our McDonald's example, our largest amount in the list was probably 75. Smallest, was probably 75. And our largest one, I think, was probably 324. And we decided for simplicity to round those into 5 different classes. And so we would take 324 minus 75 and divide it by 5, and we would round it. So it's best to round up. We don't want to be super specific on that. Now, step 3, we're going to choose the value for the lower class limit by using the minimum value or a convenient value below the minimum. That's how we got the 75. And then for our upper one, 324, we looked at our data, largest and smallest. Using the lower class limit, which we had a moment ago, our lower class limit was 75. And our class width, which is 50, we're going to construct our other ones. So our next class limit should be at 125. and keep adding 50 to it till we get all 5 of them. Then we're going to take each individual data value and put a tally mark in the appropriate class. That's how we're counting them. That's the frequency. And then we're going to list all of it in a column. On step 6, we're going to list all the lower class limits in a vertical column and enter the upper class limits. So we're basically putting it in a table now. So here's some mistakes that are very common. You got to find the correct class width and the class boundaries, and those things can be tricky. The class width, don't make the most common mistake of using the difference between the lower and upper class limit. That is not the class width. It's between the lower class limits. The class boundary, remember they split the difference between the end of one class and the beginning of the next. They're in the gaps. Most people get those confused. Now let's look at some more frequency distributions. Categorical data can also be summarized in your frequency distributions. Those are like your names, remember, categorical data. So like the colors of the M&Ms. They can go in a frequency distribution. You see how many reds, yellows, greens there are. There are also other kinds of frequency distributions, the relative frequency and cumulative frequency distributions. A relative frequency distribution, it's basically what we would call a percent distribution also. It's where each class frequency is replaced by a relative frequency or a percentage. And then how do you get that? Well, the relative frequency for a class is going to be your frequency, how many tally marks you had for the class, over the sum of all the frequencies. So that's like your total. And if you multiply that number by 100%, you'll get the percentage. And like I said, we're going to see some examples of these things. Numbers make it much better. So back to our McDonald's example. I am going to add up all the frequencies in the table. So 11 plus 24 plus 10 plus 3 plus 2. It's 35, 45, that's 50 total frequencies. That's what my denominator is going to be. And then for each class, like the first one, I have 11 in there. That's what the numerator is going to be. The next one will be 24, then 10, then 3, then 2. So 11 divided by 50 is 0.22. This is the relative frequency. And if I want it as a percent, I multiply it by 100. And look, that's what goes right there, 22%. To get the next guy, I take 24 and divide him by 50, which is going to give me 0.48. And as a decimal, look at that, 48%. So this is how we get our relative frequency table done. And the sum of the percentages in a relative frequency distribution must be very close to 100%. So these things better add up. And with rounding, they might be a little off. It might be 99.8 or something, but still close to 100%. So it's each individual frequency for the class over the total, and the total was 50 in this case. A cumulative frequency distribution is where each class is the sum of all the frequencies before it. So, back to my McDonald's example. 11's the first number, so 11 stays the same. Now 11 plus 24 is 35, and look, that's the next number. And then 35 plus 10, 35 plus 10 is 45. It's the next one. Add 3, you should get 48. Add 2, you get all 50. So you're adding all the classes above its frequencies together. That's a cumulative because it's adding up, accumulating all your frequencies. Cumulative frequency distribution. And notice how the actual labels on the class change. The first one's 75 to 124, but look how it changed to anything less than 125. The next one, it said 75 to 170, or 125 to 174. This one says anything less than 175. So you notice how the labels change for the classes as well. Now, we're going to use frequency distributions to understand our data. We want to know the distribution, like the shape, the spread of the data over the range of the values. Sometimes we want to see if it's normal distribution. That's a bell shape. There are several ways we're going to analyze our data. One is we're going to look to see, is it a normal distribution? That's a very common thing to have, and we want to make sure if we have something that's normal, it makes it easier to predict things. We're also going to do this other one, which is an analysis of the last digits. This kind of lets us know when our data we get, if it's going to be recorded or measured. So it lets us know a little bit about that. Like weights. When somebody asks my weight, I don't tell them that it's exactly 196.6, I say, somewhere around 195. I round. And so that's where we're looking at the analysis of last digits. The next thing is we're looking for gaps in our data. We need to know if there's any gaps. And sometimes we even do comparisons of our data. And we're going to look at all this evening. So first one, normal distribution. How do we know if something is normal? It's going to have a bell-shaped curve. When I say bell, I'm talking like the bell you ring. See, it's kind of a bell-shaped curve. And so the frequencies, they start out low, and then they go up high, and then they go back down low again. And it's hard to tell, but it's generally kind of symmetric on both sides. So, what does that mean? We're going to look at that shape and see if it's a normal distribution or not. So we look at this table that's given to us, and we notice that there's a maximum, and it started out low, rose up to the maximum, and then it got low again. And they seem to be about the same values. In fact, they're the exact same values, 8 on both sides, 2 on both sides. So yeah, I'd say this one's pretty normal. Now here's where we use analysis of last digits. So people took their pulse, and let's say we had numbers like 80, 70, 60. Those all end in 0, so they went in this category. 455 people had something that ended in 0. Now let's say that somebody had a pulse rate of 82, 62, or 72. Those all end in 2. So they went in that category. There were 461 of them. So what they're saying is they took everybody's pulses, wrote down their numbers, and then they looked at the last digits and counted how many have that same last digit. That's what this table is. And so when we look at it, we've got some zeros in here. Nobody ended with a 1, a 3, a 5, a 7, or a 9. They were all even numbers. So that means that more than likely they were rounding. You know, remember that where you count your pulse for like 10 seconds and then you multiply it by 6 or something like that, or maybe is it 6 seconds and then multiply by 10. That's what they probably did. They probably counted it, multiplied it by 10, and that's how they got these numbers. That's why there's not any odd numbers in there. So this one was not them counting the entire time for that. That was them rounding a little bit. And we could tell that by analyzing the digits. Not, you know, normally you should have people with pulses with anywhere between the last digit of 0 and 9. Now, are there any gaps in data? Now this one's kind of cool. People were weighing pennies. So they had some pennies that were between these weights here in the beginning. But then they had this gap here where nobody had any weights in that middle. And then back to the end, more pennies. Well, what this gap means in the fact of the pennies is back in the day, pennies used to actually have copper all the way through. And copper, as you know, has gotten to be kind of, well, expensive and valuable. People are stealing it all the time. So the pennies that were heavier, these are the heavier pennies, and those are the ones that had more copper. Then they started later on saying, well, it's cheaper and less copper needed if we make lighter pennies. And so these are the ones that are copper plated with nickel inside. So if you ever chop a penny open, you can see if it's an old penny or a new penny. Is it heavier or lighter? Now, why aren't there pennies in the middle? Because they only had the two kinds. They didn't have a mixture of pennies that was not really copper plated, but not really fully a full copper penny. They didn't have anything in between. So we had a gap in our data. Comparisons. Now these are just compared to two restaurants at their lunchtime. We already know about McDonald's over here because we've already kind of looked at him. These are his frequencies for each of the time periods at lunch. And then over here we look at Dunkin' Donuts. They are totally different kinds of restaurants. McDonald's is cooking burgers and fries. Those things take a little bit more time. So most of their frequencies are going to be in this range. But then donuts, that's probably just grabbing donuts that were made this morning off the shelf. Look where a lot of their frequencies are. That means they're faster at lunchtime, Dunkin' Donuts is, than McDonald's. But why? Probably because Dunkin' Donuts isn't cooking burgers. It's only